We know in equilibrium, electron and hole concentration are thermal equilibrium values. And we also know that we can write free electron concentration to be equal to intrinsic carrier concentration multiplied by exponential EF minus intrinsic Fermi energy level divided by kT. Similarly, hole concentration can be written as You can also see that from these two equations, we can verify the mass action law, such that Np is equal to Ni square. But the situation changes when we add excess electrons or holes, which ultimately disturbs the thermal equilibrium. In such case, Fermi energy level EF splits into two Fermi energy levels, which are EFN and EFP. These two Fermi energy levels are called as Quasi Fermi energy levels. The new free electron concentration can be written as N0 plus del N. Similarly, hole concentration can be written as P0 plus delta P. In non-equilibrium cases, we have to use quasi-Fermi energy levels to relate free electron and hole concentration with intrinsic carrier concentration. Like, free electron concentration is equal to Similarly, hole concentration can be written as Obviously, in non-equilibrium condition, mass action law is not valid. However, when we multiply the free electron and hole concentration, we will get another relation which is quite similar to mass action law. We studied this topic just because we should know how the energy band diagrams of a p-n junction are actually drawn. You know that when a p-n junction is unbiased, then the Fermi energy level is a straight line. Now, we will consider the case for forward and reverse biasing and will construct the complete energy band diagram. For that, first we are going to take the case of forward biasing. We will divide the region into three parts: depletion region, p-type region and n-type region. We will be fixing Fermi energy level in the p-type. So, we will always draw the Fermi energy level in the p-type first. Now, you know that in forward biasing, we are actually applying positive voltage in the p side of the diode. And also in the first unit, we studied that the points which are represented at lower position in the energy band diagram are actually at higher potential. So, if we have to represent Fermi energy level in the p side to be at higher potential, then we have to draw Fermi energy level in the n-type to be higher than the Fermi energy level in the p-type. In the depletion region, due to the non-equilibrium condition, Fermi energy level will split into quasi-Fermi energy levels, such that the complete Fermi energy level will look like this. Now, by drawing the conduction band and valence band energy level, we can fully construct energy band diagram of forward bias p-n junction. Similarly, we can draw the energy band diagram for a p-n junction when reverse biasing is applied. First, we are going to draw Fermi energy level in the p-type. Since we are going to apply positive voltage on the n-type region in reverse biasing, then we have to bring Fermi energy level in the n-type region downwards with respect to the Fermi energy level in the p-type region. I hope you have understood this much, that when we apply forward biasing, then the difference between the conduction band energy level is Q into V0 minus Vf. Same applies in the reverse bias case. I am hoping that you are able to recall the point which we studied in the first unit, that points which are at lower position in energy band diagram are having higher potential. Because these energy band diagrams, particularly the Fermi energy level, is drawn by keeping this particular point in our mind. This is the reason why the first unit is very important, as many topics from the first unit are directly used in other units, and you are supposed to find the relation between the different topics.